Yeah, but it's fine.
Uh, See, he is able to hear. Okay, we have to hear
We
only
could hear, but clarity இல்ல.
clarity. Yeah, தெரியலையே. So I'm
சரி
using
விட்டுருங்க. பரவாயில்ல, ஒண்ணும் பிரச்சனை இல்லை விடுங்க.
okay. The other health, I think you are all right now.
Yeah.
Sir.
I think you are all right now. You're back to normal.
Yeah.
Good, very good.
The office Monday only I'll join.
Okay.
So that's it.
So shall we start?
Yeah. So I just asked Kamalakannan to share these
Yes,
slides.
sir. Sure, sir.
So good. I'm very happy to invite Dr. Rajaram from IGCAL Kalpakam, external member for the National Committee, and Professor C. Venkateshwaran, HOD of Department of Nuclear Physics, to evaluate Mr. Kamalakannan's synopsis presentation, enabling him to submit the thesis in a stipulated time. So welcome both of you. Good morning. I think Kamalakannan can start now.
Sure, sir. Thank you, sir. Thank you so much. Sir, everyone able to see the screen?
Yes.
Yeah, it's fine.
Okay, sure, sir. Good morning to all. So my title of the presentation for my thesis work is Defect Studies in Low Energy Ion Implanted Silicon Carbide. I organized my chapters, like in introduction, so I have to introduce my material, so what I have to do and what is the output we have to gain it, and experimental methods to study the defects most probably. So my aim is to study the defects and what is the effect of the defects and how we can reduce the defects. So I have to use the Raman and positron spectroscopy technique to study the defect structures in atomic level also. So then, based on that techniques, I organized 3 major chapters. So one is I have to implant the nitrogen in the 6-SAC, and what is the effect of the implantation and what is the annealing effect of that particular one by using Raman spectroscopy. And chapter 4 is same material and implanted nitrogen and study the defects by using positron spectroscopy. And the chapter 5 is the silicon carbide material, and we have to implant aluminum and study that both the things by using positron and Raman analysis for that things, and summary and future work is chapter 6, and the publications and remaining things. So chapter 1 is a silicon carbide. So I have to use the silicon carbide material because so all the semiconductor materials is needed the electronics, all the electronics that needed the semiconductor materials. We have to use most probably in the early stages silicon and germanium. So and gallium arsenide, common semiconductors also developed later on. But
Kamalakannan,
sir,
sorry, that you minimize that tabs which are there, like sharing entire screen, that you can minimize, and
sure.
your recording, I think, so that you can pull down somewhere down,
Okay,
so
sir.
that the
Sure.
slides can be.
Sure,
Yeah,
sir. Thank you, sir.
fine.
Fine.
Thank you.
Sure, sir. So, silicon carbide, the silicon-based materials is thermally stable. It's limited at 250 degrees Celsius. But if we want to use that materials for the high temperature and high frequency applications, we can't able to go for semiconductors, silicon and germanium or gallium arsenide materials also. So, for that replacement of that particular things is to use these material for the high temperature, high frequency applications. We have to need look the different materials. So for the perfect replacement for the silicon based materials is silicon carbide, because silicon carbide is highly stable at high temperatures also, and the hardness of that material is also very high, and it's having the light wear resistance, and it having the high electron drift velocity and high electrical breakdown strength. So based on the promising properties of these silicon carbide materials, we can use various applications for that, and the development is also more is further developed by using these silicon carbide materials. So the major application for the silicon carbide, so we can go to the LED devices as field effect transistor applications also developed, and the further applications because silicon carbide having the native SiO2, okay, because SiO2 is in the dielectric material, so we can use this for the MOSFET and FIT applications also, and because of its inertness high temperatures, we can use in the furnaces and combustion engines, and it's a high it can be used in the high frequency applications, so that we have to go for the microwave and some kind of applications. So more than that, we can use silicon carbide for the cladding materials, fusion reactors, and some structural components in the fusion reactors also. And in the past moderators also recently they developed by using the silicon carbide material. So it's have the tremendous amount of applications by using the silicon carbide, and more and more devices also we can develop by using a particular system. So I have to choose the silicon carbide material, and then the total applications it's given in this particular slide. And yeah, and the impact of the silicon carbide in the market is, of course, it's gradually increasing each and every year. Of course, in 2025, so more number of replacements in the semiconductor-based things can occupied by the silicon carbide, mostly in the high power and high frequency and applications. Mostly in the extreme level, we can use this particular materials. And so we have to use the silicon carbide crystals. So first developed man-made silicon carbide is achieved by the Hutchison, but naturally it can be available. The name of that particular one is called moissanite. So because Henry Moissanite found that one, after his name they developed the things. The major problem for the silicon carbide material development is it's created the more number of defects. Most of all, micropipes is the very major problem for the silicon carbide materials. So the various crystal growth methods are developed. So in the nowadays, okay, so people are using the LED based vapor phase across method to get the low reduced micropipes defects. So one of the major applications for the silicon carbide is it's polytips actually. So okay, so around 250 more than that particular polytips are now for the silicon carbide. So we can classify that polytips by using two types. One is the alpha and the beta. So I mean the cubic and hexagonal cubic and other structures, especially hexagonal and as well as rim of metal structures, everything is we can classify that particular one. So in the silicon carbide is having the bond length between the silicon and the carbon is around 1.89 angstrom, which is highly strongly bounded between that one. So it's a very hard material usually, and the bond length between the silicon and silicon adjacent layers is 3.08 as well. We can these polytips are differ from the bilayer of the silicon and carbon usually. So that notation is given by using the Ramsel things. So a number followed by a letter. Usually the number denotes the number of bilayers, silicon and carbon like that, and the letters denotes the structure. So for example, two-way SAC, it's a two bilayers for silicon and carbon. H is the hexagonal, and for 3 it's a cubic structure, and for 3 layers of configuration for that particular one. So this can be easily explained here in this particular slide. So we can see the bilayer of silicon and carbon and silicon and carbon. So if it's going like this, A and B, A, B, A, B, A, B like that, it's of course it will give the complete hexagonal structures. And the next component we can use A, B, C, and again A, B, C, A, B, C, A, B, C. It's a cubic completely. So there is only one cubic structure will be there, and all the structures are different oriented things. And here you can see the bilayer of that A, B, C. Then again it's a form like B. So it's not going like that A, B, C, A, B, C, A, B, C, not like that. If it is turning of that particular one, so these in between the turning points, it's usually a cubic structure, and that particular turning point is hexagonal. So we can define the different polytypes by using that variation of the bilayers of that system. So I am using the 6SAC. 6SAC based on A, B, C. And A, C, I mean here we can see the turning points is from the A. I mean from the fourth layer the turning point is available, and after that the continuity is gives completely 6 layers can determine as. So it's give us as the hexagonal. So then the total notations for the polytypes is given this particular one. So the Ramsel notation we can define already, and the ABC notation is given, and the turning points. Okay, so that's hexagonal, and in between the turning points cubic. So the major important things is in the hexagonality means if hexagonal increases, the band gap of the material is increases, because so electrically the silicon carbide is having the different property for the different polytypes. So I am using success, so which is having the around 3.2 electron volt band gap of the material. So it's pretty indirect band gap material. So then, so for the usage, I mean, to improve the usage of the SAC, we have to implant the, we have to introduce the dopants. So usually in the thermal-based doping methods they followed, but in the silicon carbide materials, especially hard materials, we can't dope the high concentration of the ions. Okay, so because it's a saturation limit and thermally it's stabilized. So, but we need very high concentrations to get the various applications. So I have to go the another method, so which is called implantation. So because so implantations we can dope even at very high concentration also we can achieve, and as well as in the diffusion process it's a complete system. The based on the diffusion, so the doping ions is completely distributed, but in the implantations we can control the energy to depth of particle level, and we can make the layer by layer format also. So PN, PAM structures also we can get it, but in the diffusion process we can most probably it's not possible for the case. So implantation have the major advantages than the comparatively the diffusion process, especially for the hard materials. But the implantations mostly it's created the defects, especially the point defects, and as well as the die vacancy depends on the material structures. So that's the major problem for the implantations. But we have to reduce the implantation by using the methods. Most probably we have to anneal the material after the implantations. So what is the effect of the implantation, and what is the effect of annealing after that? We have to study the complete scenario, right? So and another one of important findings we have to determine by the silicon carbide. So especially the defects created in the silicon carbide is used in the various applications. Most probably the ion vacancy complexes, which is vacancy of the silicon and what kind of ions we can implant it. So this complex will be created, and these complexes is used as a quantum computing applications most probably, and some kind of defects which having the spin coherence property that's also used as a synchronics and photonic applications also. So identify the particular type of the defect and what is the depth and where is the position and what is the structure. So and the quantification of defects, that's very important to the applications of the various things. So I have to plan to study the defects in the localized defect as well as the bulk level of that system, and as well as the atomic level defects by using the Raman and fast annealing spectroscopy technique. So especially I have to use the Doppler bonding spectroscopy technique to determine the defects in the depth-wise analysis. So and after the data collecting from the fast analysis, we have to use the variable range fast and fit to find the particular type of the defect, and especially we have to correlate it with the previously reported things and some kind of calculation, theoretical calculation we done these things. So typical fast analysis spectroscopy technique shown in here. And so according to these things, my main objective of the work is we have to fabricate the N-type and P-type materials by implanting nitrogen and aluminum. So nitrogen is most probably forms the N-type material, and aluminum implantations gives the P-type material. So and the selective depth and with the high concentrations we have to use in this particular system, and we are using the semi-insulating materials. So because of the various applications, because semi-insulating material is needed for the FET and MOSFET applications especially, so that we have to get the semi-insulating material for the SACC. And what is the changes from the crystalline to disorder after implantation, and identification of defects at the atomic level by Raman and variable range fast and spectroscopy technique we done, and so modeling of the data which is analyzed from the fast analysis spectroscopy, and identification of the particular type of the defect by web-fit methods, and the detailed study is also expected to find out the role of annealing and according to the defect recovery and activation of the defects and recalculation of the materials. So we done that particular things. So this is the main objective of my work. My first chapter included this slicing of the SAC. So we got the commercial grade SAC from the University of Carolina, and the cutting of the SAC is very difficult to that particular because of its hardness. So we have to modify the base which is available in our laboratory. So low speed diamonds are cutting machines. We have to modify the base and we have to cut that particular one. Of course, some very good cutting we got in this particular things. The slating direction is given here. So from the secondary plot, it's a primary plot. We have to cut in the 1 and 2 bar 0 directions to get the perfect one. So the samples which is cut in the 1 cross 1 centimeter square, which is easily to mount in the implantation chamber. And the chapter 2 is implantation and range and pH technique calculations. So as we discussed, so we have to implant the nitrogen aluminum with the different ion and energy. So these are the major components of the ion implantation technique. So most probably ion source and accelerator targets, target chamber we have to use. So implantation is most probably the energy range is around some 100 kiloelectron volt to some few MeV. So below that, usually the people are telling that it's a what's the epitaxial growth, simply like that. Okay, so it means doping of that. Yeah, of course, it's some kind of doping in the top layer only. So we have to go in the particular depth. So we are planning for some electron volt to some kiloelectron volt to some MeV. Before implantation, we have to study the depth of the material, because we have to create the different N and P layers. So the energy and the depth must be previously determined to go before the implantation. So for that case, at the range distribution, range calculation, we have to use the stopping and ranges of ions in matter and transport of ions in matter. So from both the simulation softwares, it's available. So Monte Carlo based things. So from this, we have to determine the implantation depth, as well as the collision events and damage events, as well as the concentration of the doping. So how much we have to get that particular one. So these are the shim main badge of that system. So we can directly select and give the ion energy of that particular one. It will give the complete report of the range from this particular one. So I have to choose the 130 keV because I need to get around 200 nanometer of the system. So even though that's projected in the staggering limestone staggering, also it will be there. So so it will give us some kind of layer structures of that. I mean some thickness of the layer we got that implanted ions. And this is a transport of ions in matter, the second one. So from this one we can determine the especially the range distribution in the two-dimensional plot. From this data we have to get that analyze the range and distribution of the range, as well as the concentration of the ions and the collision events. So everything we can calculate from the trim report. So both the analysis from this particular system, we have to go for the ion implantation. So so these are the accelerators we have to use for the implantations. So it's available in the IG Kalpakam. So for the aluminum implantations, we have to go 1.7 MV tandem accelerator. So aluminum I have to implant around 400 keV of the aluminum energy, and for the gaseous ion implanted we have to use the 150 keV ion implanted. So I have to go at maximum 130 keV of the energy of the nitrogen implantation. So both implantations done here. These are the things we have to use that particular one. So implantation, everything is given. So these are stream reports from the before implantations. So from the knowledge we have to get to that implantation depth. So and I have to study the defects after the implantation. Because implantation created the different kind of defects most probably. So I have to use the past analysis spectroscopy technique. So so major analysis techniques are past analysis techniques are three. So angular correlation, lifetime, and the Doppler bonding spectroscopy technique. So among them you have to I'm planning to do the Doppler bonding spectroscopy. So especially I have to use the variable energy past analysis spectroscopy. So everything the most probably this Doppler bonding is based on the electromagnetic distribution of the materials. So it's find the electromagnetic variations in the defect states, and as well as the material natural materials. So as we know, the defect, suppose void is there, the electromagnetic density is lesser than particular things, so that the past time can stay more time in this particular one. After that it will be annihilated with the electrons. So lifetime is also increases the system, as well as the depends on the electromagnetic density variations, the energy and the momentum of that particular things is also varying. So so I have to use the so general concept of a particular one. So the electron pass trans annihilated give the 511 keV, and plus or minus delta V is the broadening of the system, depends on the variation of the electron momentum in the defect state. So from the analysis I have to get the S parameter, which is called the output is given like this. okay, for the Doppler binding spectroscopy. So this is separated in the two ways. One is the S parameter and another is W parameter. The W parameter is based on the wing area, okay, and S parameter is in the central region. So S parameter is most probably it's sensitive for the open type of the defects, and the W parameter is mostly sensitive to the chemical surrounding of the annihilation site. So we have to get both the things as S and W parameter differently for the different energy, and these are the Doppler bonding spectroscopy, variable energy spectroscopy, which is available in the IGCAR. So typical compounds are shown here. So the sodium 22 is used as a passed-on source, and so after the the output of the positron after from the moderator, okay, we have to get the slow first turn for that particular things, and we have to accelerate again from the starting from 0.2 keV to 22 keV, because after the moderator, of course, the energy of the positron is completely reduced for the particular. So from the sodium 22 we have to got 0.546 MeV of the energy. So because I have to analyze the depth wise, which means I need to get from 0 to the particular energy of the system. So my implantation depth is around 200 and 400, 600 nanometer only. So of course 22 keV is enough to find the complete system of the material. So after that it is implanted. So depends on the energy value, it implanted the particular depth, and after that is find the vacancies. Okay, so where is the momentum atom density is low, to find there, and it will be annihilated from the electrons which is available in this particular region. So it is annihilated with respect to 511 keV. If both the depends on the energy variation, 511 keV plus or minus delta V. So that is plotted with the S and energy value, and that's S parameter completely for different energy. We have to plot that and getting the output of that system. So these are the variable energy setup output. So the implanted depth can be calculated, past implanted depth can be calculated by using this particular formula, which is called x equal to AE per n divided by rho. Rho is the density of the material. So A is constant for materials. You then get A equal to 40, and energy E which we have to implanted, N equal to usually 1.7 for that system. And so the energy of the positron is from 0.2 to 22 keV. It's implanted. So it's around so first is, after that it's thermalized. Okay, so I mean the energy of the implantation is completely thermalized, and after that it find the vacancy which is available in the system. It's diffused. It's around about plus or minus 100 nanometer. So it's a typical range of that system, and after that it will be annihilated with electrons. Okay, natural electrons, and the information of the system is given and plotted like this. Okay, from this parameter with respect to the energy, and the mean implanted depth is also shown in the x-axis in the top layer. So that's calculated from the equivalent profile. So this is fitted, and we have to get the defects of particular system. So Raman spectroscopy, as we know, so that's simply localized defect structure we have to determine, and so my chapter 3 we have to go that particular one, which means nidison implanted and recursive probed by Raman analysis. So this is my methodology we have to use, and 130 kV of the nidison is applied to the CCAC, and the depth of that particular one is calculated from stream analysis around 200 plus or minus 15 nanometer, and two dose I have to select. So one is 10 per 15 and 10 per 16 ions per centimeter square, and by using the 150 kV gaseous ion implanted. So and after that it's completely amorphized from top layer to the particular depth. And after that we have to annihilate that particular system with the 800,000 degrees Celsius, and it's completely recrystallized, and one defect recovery we got in that particular one. And the N layer, so of course the ions diffused, implant ions diffused, and it will be stable in that particular lattice site, especially the nidison ion replaced in the carbon site, and it sit in the that particular things, and it may be forms as the N layer. So we have to, if we want to activate that furthermore, we have to annihilate further degree. The SIM calculated the range plot, and as well as the vacancies which is created silicon and carbon vacancies plotted in this particular one. So this data from the SIM analysis. So especially from here we can got the depth of that nidison implanted ions is around 200 plus or minus 50 nanometer. So maximum it can go around 300 nanometer. Okay, it's shown in the x-axis. And the silicon vacancy and carbon vacancy is also given. Silicon vacancy is dominated most probably from the analysis of the system. The vacancies is created, the peak vacancy of the system is around before the ion range, of course. So that's also we can determine from the particular one. So this is correlated with the Raman analysis also. So this is the my Raman result from the pristine, which means unimplanted sample to the implanted sample. So the ACN15 is the 10 per 15 dose sample, and it's ACN15A is annealed with respect to 800 degrees Celsius, and 16 is 16 dose, and 16A is 800 degrees Celsius annealed samples. And yeah, all the prominent mode in the pristine samples we got. And the first order and second order Raman modes also perfectly analyzed in this particular one. So every data are normalized, area normalized to compare the system different oriented things. And after implantation for the low dose samples, we can see all the prominent modes are available, but even though it having some kind of disorder peaks also there. And so if you are implanted the further mode for the 16 samples, so especially the prominent Raman modes is not completely available. Of course, it's available in the first order Raman modes, especially 788 centimeter inverse, but we can't see the E to TA mode especially because the highly disordered range is shown that particular one. So after annealing, of course, the modes are regained in the particular system, even though we can't get the complete intensity of the modes as compared with the pristine, but which shows that this 800 degrees Celsius annealing is not completely recover the defects. Okay, so the modes are identified from the as phonon modes A1, E1, E2, and everything is compared with the literatures, and everything is determined. Okay, so our aim is we have to determine the implanted ions, and from the at 200 nanometers maximum, so that we have to use the jet scan Raman spectroscopy technique to determine the variation of that system. Okay, we can see so this is the top one in our left hand one. So ACN15 we can see the implantation gives the that means the surface layer is already been determined. So after 1 micrometer, okay, so the intensity of the system is decreased. It shows that the damages is increased if you are going from top to from surface to the range. Of course, our resolution for the Raman spectroscopy is around 1 micrometer, so that we have to slide to the 1 micrometer. So intensity decreases in the sense from top to the particular range, the defects, the damage increases, because most probably that's the ion range. So that's given in the particular one. So in the 16 samples also the same scenario we have to get it. But in the after annealing, okay, we can see the intensity of the surface is lesser than the particular range, which means of course the all the prominent modes are we got, but even though we can compare with the 15 and 15 surface and 15A samples, we can see the intensity decreases with respect to the depth. Okay, so it shows that say all the implanted ions, the defects, okay, simply the created defects, it's moved towards to the surface, and it can be migrated there and agglomerated, and it show the higher damages in the surface. Okay, so if you are annealing furthermore, okay, of course we will get the defect recovery we obtain in the depth, but even though in the surface it's agglomerate defects, it's analyzed for the particular system. So in the 16 samples also we got the same things. Okay. So the increased intensity deep than the surface, which is indicated the vacancy agglomeration, which gets triggered and diffused back to the surface after the annealing. Furthermore, we have to get that up to 5 micrometer what is happening for the high dose samples. Okay, so for that case we can see the left hand side is the higher ACN 16 sample from the surface to the 5 micrometer. We can see the intensity of the system. Okay, from surface to 1 micrometer is very less, and after that we can see the intensity increases, which shows that the defects for the implanted things is created up to 1 micrometer only. So but after the annealing, we can see the at 1 micrometer we got all the the high intense peaks, even the second order Raman modes also having the second order disorder Raman modes is not available in the 1 micrometer. It shows that the defects are agglomerated at the surface, and after that the intensity is gradually increases of the system. We are interested for the A1 LO mode, which is in around that 966 nanometer. So because it's a phonon mode is usually the frequency of the phonon mode defects is easily correlated, it gives that defects of the success of the system. So mostly it's defects disorders is affected the launched optical phonon mode. So we have to get the launched optical phonon mode to determine the disorder damage. That is that optical phonon mode A1LO mode we can identify it by using the polarization and depolarization of the Raman peaks, the particular one. Okay, so for the different configuration of the input we can get it A1LO mode suppressor, and the remaining structures we can get high intensity peak. Okay, so but the variation of the 1 minus A norm, which is measure of the damage. So of course we can see these annealed samples for the 15, 16 and 1 micrometer on surface. So every modes at 1 micrometer after the annealing, of course it's a disorder that decreases, which shows that defects are recovered in this particular system. Okay, so in the SEN 15 and 16 sample at 1 micrometer, so both the values are, I mean the damage measure of damage is both having the same value, which shows that of course the damage are saturated, which means furthermore, even though if we are giving that particular system, the damage is of course it's maximum damage we attained. So after the annealing for the 16 sample, we can see at 1 micrometer, of course it's recovered in this particular one, and 15 samples also recovered in the system. Okay, completely. The recovery is also showing, and what is the damage, measure of the damage is also identified by using the variation of the A1LO phonon mode, right? Then the intensity of the system, so from the surface to the 5 micrometer, of course it increases after annealing the samples. Of course it's at 5 micrometer, the intensity is almost reached the Preston value. So which means the defects is not there completely in the 5 micrometer depth. So the complete other parameter mode intensity is also shown in this particular table. So everything is area normalized one to compare with the all the samples, and it's a graphical representation of the system. So it's recovered in the deep region, but in the surface we have to get the agglomerated the defects. That's also identified by using the Raman particular mode, A1LO mode, and all the modes also showing the same scenario. So this is the conclusion of the things. So of course we achieved the 130 kV nights implanted silicon carbide material, and the amorphized and accumulation of the defects after the annealing is analyzed by the Raman analysis, and of course the disappearance of all the phonon modes, okay, in the high dose samples show the higher damage, and after the annealing we have regained all the modes, which shows that defect recovered, and as well as recrystallizations also induced. So especially we have to plan for 18 degrees Celsius, in the sense so of course that 18 degrees Celsius is the threshold temperature to cover the defects usually for the silicon carbide system. So we have to go in that particular system directly, particular temperature. So then so I can do the jet scan analysis of the Raman spectroscopy. So all the defects are confined in the surface after annealing, in the recrystallizations induced in the deep. So everything is analyzed in this particular one. So the next chapter is we have to analyze the defects, the atomic level defects by the past annihilation techniques for the same system. The same methodology we have to follow, but in the stream analysis we have to use the extra for the Nekovian profile for the 6 keV positron energy. So that using that particular equations. So it's around 6 keV positron. If you are use that particular system, almost it's matched the peak value of the system, right? So this is the past nice parameter value. So as we see, the bottom on black color is the percent S parameter for the different energy, and the depth of that particular system is also given. So of course it's gradually it's decreasing if you are increasing the past energy, which shows the defect free nature of the system. And if S parameter increases, now of course the open volume type of the defects, vacant stable defects increases. So if you want to get furthermore the information from that particular system, now we have to fit this one by using the varied branch past and fit. So in the percent sample we have to use the single layer fit, because it's we are considered that the percent sample is having the homogeneous structure, so that we have to use the single layer fit, which gives the fitting resulted the S values around 0.546 and plus or minus 0.002, and the diffusion length of the positron. Okay, so after implantation, so the positron can be diffused. Okay, and it wants to find any defects which is present in the particular one. So typical diffusion is around plus or minus 100 nanometer, but of course if diffusion value is higher now, so defects is not there, of course. So we are considering that it's a percent sample is it's defect free, of course, almost defect free samples. Of course, we are identified that from the Raman peaks also. Of course, we are getting the fine peaks. So that L plus value, which is obtained from the variable energy constant fit, is around 215 plus or 6 nanometers. More than 100 nanometer, of course, it's a very well-known value for the defect-free nature of the system. And after implantations, so we have to fit the system. We are separated these layers by using the two regions. So one is the damage and unimplanted regions. So the damage region separations, everything is we can done from the variable energy constant fit techniques. So in the damage region, it's around up to the depth what we have to done, and the range of the ions, as well as the unimplanted regions is the remaining region. So we have to fit the based on that particular idea and to determine the system. So if you are so the fitting resulted of the SCN15 and SCN15A8 and 8, which means 1000 degrees Celsius annealed and 800 and implanted. And compared with the pristine, 16 samples also shown here. The next one is the box profile, which is the fitting result of the things. So which means a damage profile of the system completely. We can identify the system. Okay. So as we know, all the pristine samples fitted with the single layer, and all the implanted and annealed samples fitted with the two layers. So for the high dose samples, especially and annealed samples also, if you are fitted that particular system without increasing the electric field strength, because implantation is introduced more number of electric layers, electric fields in between the states. This especially in silicon carbide system, it produces like that. So it affects the positron diffusion of the system completely. So that if you are include that, if you are not include the electric field strength in the variable energy positron fit, it gives the very low diffuse length of the positron, as well as the boundary layer is also confined towards the surface. Okay, so it's not accepted in that particular system. So that we have to introduce the electric field strength usually. So if you are introduce the electric field strength of the surface region only, which means in the implanted region, so of course the diffusion length increases, as well as the boundary width is also equal with the implanted range as we calculate the stream, so that it's a highly it's needed to increase the electric field strength in the fitting. So all the fitting results are included in the electric field strength. So the results including the electric field strength shown here. So if you are not included now, of course the diffuse length around 0.2 nanometer. Okay, so around the very minimum. So it's not 0.2 nanometer of the diffuse length, and as well as the upper boundary layer is also shifted towards the surface. Around it's around 130 nanometer, of course. But our implanted region is around 250 nanometer. So that we have to introduce the electric field. Of course, invert directed electric field obtained positive directed, and the upper boundary layer is around increased around 256 nanometer. So of course, it's highly applicable with our implanted range. So furthermore, the other parameters, okay, the S and S parameters for the different regions obtained. So from that particular systems, we have to compare the S parameters with the especially normalized S parameter with the previously available literatures and everything, and of course most probably the values which we obtained is around 1.06 and 1.09. The normalized S parameter values of the system. Of course, it's usually it's give the die vacancies. If it is 1.09, usually it's undefined larger vacancies. Okay, so everything is identified for the system. So and dry vacancy and larger voids and vacancy agglomerated systems also determined. So we can see from this particular plot. So from the pristine, if you are implanted, of course the S values increases for the SCN15, which is blue color, and after annealing at 80 degrees Celsius, then the surface S values increases, but in the deep region around more than 250 nanometer, so around that particular region the S values decreases, shows that recrystallization induced in the deep region but agglomeration induced in the surface region. And if you are increased further temperature, for the same scenario is also we got it, but further decrease in the deep region, which means so we are approaching to the recrystallization in the near to the pristine, of course, and the very low value of the S value in the deep region, then the pristine means any intensity defects is available. That's also it's annealed for the particle system. And similarly in SN16 also we got if you are annealed higher temperature, of course the S parameter for the surface is increased, which shows the agglomeration and diffusion of the defects towards the surface. But in the deep region, it's of course a decrease in the sense recrystallization of this recrystallization induced in the deep region, everything. So the box profiles also we can see. So the L value, which is called diffusion length of the implanted samples, of course from 215 nanometer to 101 nanometers, it's a decrease in the sense, of course the diffusion length decreases, shows the defects completely. And similarly if you are annealing that particular system, in the surface region the diffusion length also decreases on 17 and 16 further decreased, and the boundary width is also reduced towards the surface. So if you go furthermore around 1200 or 1300 degrees Celsius also, the same scenario we can got it around the diffusion length is decreased diffusion length, as well as the surface region is confined. That means the damage is confined towards the surface. So similarly we can got it the 16 samples also. So I mean decreased diffusion length as well as of course decreased diffusion length as well as decreased boundary width towards the surface. So these are the results we have to obtain in the particular one, and particular type of defects also identified. So the complete table we can see the scenario of the system. So from SN15, 15A8 in the surface region we can see the S values increases, and from 16A8 which means it's 16A8 only decrease in the sense of course we are approaching the states like amorphized and disorder, highly disorder, and we have the reverse path of the systems also we obtain. Of course in SN16A10 maybe it's created more number of complexes like vacancy and ion complexes. Usually nitrogen ion complex most probably is easily formed. So and after the further annealing it can be the relaxation may be happened to increase in the S value in the surface. But anyway the defects it's diffused towards the surface, increase in the S value. The further results we have obtained this particular things, and all the values are included except SN15, because SN15 is not the electric field inclusion because we got that boundary with around 250 nanometer. But further another samples we have to include the electric field strength, which shows that the importance of the the ions, and as well as the activation of the ions is also shown in this particular one, because we are annealing. So the nitrogen ions will be activated in the system, right? And the S by S reference value, which means normalized S parameter value, which is also given, and we can compare this as S by S value to the particular type of the defects. Most probably the SN15A8 the die vacancy VSA VC is created probably, and SN15 is also around die vacancy only, and SN16 is larger voids especially, and 1.137 for the SN16A10 it's a highly agglomerated undefined very larger voids, because it's a higher annealing temperature as well as high dose samples. So the every parameter is shown here. So the S and W value, the plot with respect to the W parameter. Okay, W parameter with respect to the energy is also same what we got in the S parameter. So similar concept, because but W parameter having the what is that? If S parameter increases, W parameter decreases. Okay, like that. Okay, it's actually. So similarly, we can got the same result from the W parameter. W parameter is most probably in the chemical surrounding system, and that's also given here. And S versus SW parameter, we have to determine from this particular system the how many type of the defects also there. Okay, of course the S and SW value, SW plot is showing that the scattered points of that system. Of course we are trying to plot that things. Of course it's two type of defects always, as well as it's inhomogeneous type of defects. More number of defects are created by the silicon carbide system. So especially for the two layers means, two lines means two types of defects. Okay, so one is the implanted region, another is unimplanted region. So what are the types is also shown here. And the furthermore the temperature versus all other the positron fit parameters is shown here. So increase in the S parameter shows the increase in the defect type, and decreasing in the L value, and decreasing in the boundary sense, which means it's a boundary value is decreases, it's going towards the surface. So it's confined for the increasing in the annealing temperature. So the comparison table is also shown here. So the So furthermore, this schematic illustration of the system. Okay, so after annealing 1000 degrees Celsius, so we can see the deep region is recrystallized. In the top region only it's agglomerated defects, which shows the lesser L value as well as the boundary is also confined towards the surface. So this is comparable with the Raman spectroscopy results also we obtained in the previous chapter. So of course, so the same structure only we got it. The conclusion of the particular chapter is shown here. So the requirement of the electric field, finally it's in the fitting method, which is supported by the activation of the charge carriers as well as evidence of the defect signature and region modification. Especially it's invert direct electric field is identified in the system, and in the 1000 degrees Celsius annealing, of course, decreasing the S value in the deep region shows the recrystallization obtained. So furthermore, we have to if we anneal furthermore now, okay, of course, the defect migrated further towards the surface, may be agglomerated and further increase the S value in the top region only, but in the deep region the recrystallizations can be obtained. And so the next one is aluminum implantation and defect recovery in the same system, and we studied both the things in Raman and Posita in this particular chapter, and the similar scenario, but aluminum is implanted with 3 doses around 10 for 14, 15 and 16, and it's 400 keV. The stream calculated range is around 600 nanometer. So this is done by the 1.7 MV Tantan accelerator. Okay, so previous one is the gases and implanted. This is Tantan accelerator. So what is the range and the constants also we can determine, and everything we determine by the stream analysis. The stream report shown here, and of course vacancy is also created before the ion range. So ion range is maximum around 600 nanometer. So that's shown in this particular system. And this is the past S parameter for the assumed samples. Of course, S value increases, defects also increases in the surface up to the range. Ion depth increases, and if you are going furthermore around even 1200 nanometers, also it's not matched with the diffusion sample. It shows the diffusion of the positive. It's around 200 nanometers diffused, so that so the diffusion also is important to increase the values of that S value of even further beyond the depth. So as we discussed, the single layer fit is obtained from the same system, and for the implanted samples we have to use the 3 regions to get the good fit, and surface and damage and undamaged region is also shown from this particular one. And of course, all the implanted samples is fitted with the web fit, including the electric field strength. So because as we discussed, the absence of the field which gives the very low diffusion length, as well as the boundary is also showing the very low. So of course we need to get the boundary with this around implanted region, so that we have to include all the samples are included with the electric field strength. Right. So the result, okay, which we obtained after the past implantation and fit analysis shown here. Of course, the S parameter increases and vacancy also increases, and the electric field which is included in this particular system is also shown here, and S base reference which is correlated with the vacancy type of the vacancy most probably. So from the range 1.057 to 1.67, so die vacancy. Okay, so here 1.067 is CAL15 most probably created the die vacancy type of the defects, and in the surface, in the damage regions also, in the it's around die vacancy type of the defects, and of course if we are going with more than 1.1, it's undefined larger voids. Of course we can't determine the particular system. Maybe it's highly agglomerated defects available, more than some n number of die vacancies also agglomerated in the system, and everything is calculated, and we can compare with that particular one, right? So these are the annealed samples and implanted annealed samples parameter compared with the persistent samples. Of course, so as we discussed in the SEN, nitrogen implanted samples, it's a similar scenario. If we are annealing the system with 800,000 degrees Celsius, of course the S value increases in the top region, and in the deep region, of course, it decreases. We can obtain the same scenario for all the samples, which shows that recrystallization is induced, but agglomeration of the defects is in the surface region. So we have to fit that particular system and get the type of the defect, and as well as the agglomerations of the range, I mean the boundary of the agglomerated defects also we determine. So this is fitted with the 3-layer as we done in the assembled ensembles. Here is also we done in the 3-layer region. So the every parameters and what are the results obtained in this particular one is shown in the particular table. So for the ACAL 14, 48, 48 and the increase in the S value, decrease in the S value in the deep region and top regions also shown here, and S base reference also given for the type of the defects. And so all the results and which is compared with the previous things is as the same results also we got in this particular one. But here is also the same kind of things, which means complex also may be created in the 16 samples, which shows that you can see ACN 16 is showing the higher S value, and after ACAL A8 of course it must be increases, which shows that it must be increases, which means agglomeration defects. But of course we are decreasing the S value, maybe it's possible of the complexes, and after further annealing it's a complexes may be relaxed in this particular one to increase the further S value increased for the higher temperatures. But even if you are going the higher temperatures, of course agglomeration happening. So of course we are determining the changes from the amorphous disorder, highly disorder to the what is that, to the recrystallizations. Reverse path is also be done. Why we can track this particular system. So, but of course it's too difficult to determine the particular scenario for the silicon carbide material, because past and behavior is very different in this particular things. So of course the web fit past profile, I mean box profile of the system. So what the S and boundary values is shown in the table for all the samples shown here. And so again the Raman analysis for the aluminum implanted, of course they same things as what we obtained in the Nidus implantation. But even though in SCN 15 samples, as implanted samples, we didn't got any prominent peak, which shows that highly it's amorphous nature we got it, which means highly disordered state, because of the aluminum is having the highest mass, okay, compared to the Nidus. Okay, so aluminum is created more damages. Of course DPA value is also very higher compared to the Nidus. So for the 16, the disorder peaks further increased. So but annealing after the 800 degrees Celsius, we got it around all the peaks also we got it. But even though inclusion of the amorphous peaks also we got it, which shows that the annealing is not completely reduced the defects for the system. Of course we have to go around 1700 degrees Celsius for the complete recovery of the defects in the surface regions also. Okay, so that's we got in this particular one. And of course the depth profile of the system from the surface to even at 500 nanometers also we didn't got any peaks, which shows that it's a highly opaque material, because after the aluminum implantations the depth profile is not highly achievable for the system. But even after annealing, of course the defects are recovered, so completely we got it the prominent peaks for all the systems. But in the surface the surface to 1 micrometer, of course we can see in 1 micrometer the amorphous peak is not available, which shows that defects are recovered, but the surface is not recovered in the sense it's agglomerated happening in this particular system. This is also compared with the what is that, in the past annealing spectroscopy technique, which shows that the highest S value in the surface region only, but deep region we got it lowest S value. So these are the important facts we determined. And so the conclusions, and similarly the damages, okay, which is created by the aluminum implantations, is studied by the Raman and fast and spectroscopy technique. And annealing, okay, of course it's a migrate of the defects is it's happened. So if for the 1008 degrees Celsius annealing, but the deep region is covered. Okay, that's analyzed by using both the techniques, and the peak variations and the value, which is S value variations, and everything is compared. So the requirement of the electric field strength in the fast and fit, which shows that the defect activation and carrier activation as well as the defect signature and layer modification, everything you can use it by using the table we determine that particular one. And the type of the defect is also identified by the S by S reference value. So most probably in the surface it's created it's a larger unvoid, larger defects, undefined defects, but the deep regions die vacancy mostly created. And after any the further increasing in the surface S value, which shows that agglomeration of the defects and the deep regions decreased. And so further work is we have to implant the another material, another ion for the already implanted ions, which shows that so already we identified the nitrogen implanted and aluminum implanted for the different set of the samples. So for the nitrogen implanted we have to implant the aluminum ions, okay, to get the PN layers, okay, like that. And so if any I layers also we can create PAN layers also by implanting oxygen ions, okay. So further we have to only in the same system to form the layer structures and for the many more applications like FET and MOSFET and some microwave applications. And here the each and every stages we have to determine the fast and Raman spectroscopy technique, and the range, ion range, the desired range, which is already completed around 200 nanometer. For the nitrogen, for aluminum it's 500 plus or minus 100, which means 600 nanometer maximum. And we have to implant the another ions, okay, which means in nitrogen now we have to implant aluminum to make p-type layer, so it must be lower than that 200 nanometer. So that range, everything is calculated already in the stream analysis. So of course if 180 kV of aluminum ions now it's around form 200, okay, it's around 50 means it's around 150 nanometer will be formed. So the same dose and everything we have to do that particular one. This is the one to form the NP layer or aluminum, which shows the nitrogen aluminum layers like that. And after recrystallization, so we have to get the activation of the system. So completely this is the complete feature what we have to do. And yeah, these are the publications we got in the system. And so based on the different chapters, 3 chapters, and conference proceedings also shown here, and various conferences attended. So and which is related to some kind of schools which is available in the UAC, so that's also attended. And we acknowledge the UGCD ACSR for the fund, and as well as IG Kalpakam for the work. And thank you sir.
Good. Nice work. Yeah.
Rajaram, please go ahead.
Okay, so yes, I'm starting. So you started with introduction, so where you have shown positron annihilation spectroscopy, and then you try to show the Doppler broadening.
Yes sir.
But you have shown the coincidence Doppler, which you never used, right?
Yes sir, just for
Then
typical.
why are you showing that? Typical means, see, whatever, see, you have to restrict to your domain.
Okay.
Don't use something which is typical from internet and then put it.
Okay.
So wherever it is required, you use the actual experimental setups which you have used. Okay. So this is wrong. You cannot put this, and you never discussed coincidence Doppler in your whole
yes.
You are not going to make any presentation on that.
Okay.
So that is one observation. Then coming to experimental, again accelerator, you try to put schematic of what you have used. Don't again use the internet stuff. You will have many variants. Okay, so the accelerator schematic of whatever you are having, you put it. It's not that it is a repetition. Okay. So or you can make this as a schematic in a block diagram part. That is also fine. Okay. So then positron and experimental part is okay. So I have no comment on that. But you have one full chapter based on Raman, but you have not shown your Raman spectroscopy, your even heating stage, or your whatever the schematic of how the Raman measurement is done. So those you have to have at least couple of slides on Raman spectroscopy in experimental part of your presentation.
Raman system, well-known system, so that I didn't discuss.
No. It is not. It is positron also is well known. Okay.
Okay, sir.
So accelerator is also well known. So you have used and you restrict. Don't go to internet stuff.
Okay, sir.
You restrict.
Sure.
I have the schematic and photographs will be there. You can use it. Okay. So
Okay,
you have
sir.
to
Sure,
ask.
sir.
So you have to take and then put it. Don't try to bypass and then okay, I will not ask. I will put from internet. No. Okay. And
Sure, sir.
you always restrict to what you are using, so
Okay,
that
sir.
you will
Okay.
not have any complications. Okay.
Okay, sir. Sure, sir.
Then what? Okay, so when you are introducing Raman, you should also show some schematic or that you can get from literature,
Okay.
silicon first order, second order peaks, and A spline.
Okay, sir. Sure, sir.
Okay,
Okay, sir.
because you are discussing about first order, second order
Yes, sir.
for SIC, but
Yes, sir.
for simple case silicon, you can take what is the first order, second order, how they are coming. So you have to explain.
Okay, sir. Sure, sir.
Okay, so then somewhere, okay, so one more thing you check, you keep because maybe you wanted to rush it, so you are keep telling same system. Don't use it. You
Okay.
say silicon carbide. Even if you are not saying 6H, all the stuff, you say on silicon carbide. You
Okay.
just okay.
Okay.
No
Okay.
same system business
Oh,
because
okay,
we
sir.
don't know what is same system. Because you will
Okay.
forget after second chapter or third chapter. If you go to fifth chapter, what is the same system, you will not know.
Okay. Okay. Okay.
Then you are somewhere you mentioned, I think maybe in chapter 3, that start of chapter 3, sorry, chapter 4, that first one diffusion length is 0.2 nanometer.
L plus value. Yes, sir. No, that's in third chapter, I think so.
No. Sir is asking 0.2
First,
nanometer we have mentioned. Why? What is it?
Yes, sir. Yes, sir. Yes, sir.
when you introduced the postron web fitting,
Yes, sir.
and in fact, you have shown the raw data from web fit
From
result.
repeat result, yes, sir.
Where is it?
This one.
Okay.
This one.
Okay.
Yes, sir.
Isn't it? So, what is 0.2 nanometer diffusion length?
Yes, sir.
We never discuss 0.2 nanometer. You have the diffusion length typical of defect. It will be about 10 to 20 nanometers.
Yes,
We
sir.
can talk.
Yes.
Okay. So then, where from this 0.2 nanometer came?
Of course,
Which
yes, sir.
you have to see. When you
Importance
are
of
talking.
electric field.
Okay. So the
Okay.
fitting combination of so many parameters, you may
Yes.
end up in some numbers. So you have to be realistic.
Okay.
Okay. Yeah, typical defect-free diffusion length is about 200 to 300
Yes.
nanometer. Okay.
Yes. Yes.
When we have fully saturation defect trapping, then you can have at the maximum 10 to 20 nanometer as a typical diffusion length.
Yes. Yes.
Okay.
Yes.
So you cannot just like make some statement. Yeah, see, many if you go to tell in the your paper, the past run reviewer will trash you. Okay.
Okay.
And also, why you want to show the webfit result as a snapshot? You want to show a layer, then you have the numbers. You add some other table where it is very clean. So the
Okay.
whenever you are doing fitting,
Okay.
it will always give many number of decimal points.
Yes.
And also the way it is shown, you can see 10 power 4, all those things. It is you have to have the normal method of putting your S parameter or your diffusion length, convert that and then show as a table.
Okay. Okay.
We are
Okay.
not asking whether you have done web fit correctly or not.
Okay.
We are not,
Okay.
from this we cannot even tell whether you have done correctly or not.
Okay.
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 Why do you want to show that? Because you are complicating by showing all this.
Okay, sir. Okay.
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 And you have in one table you have used 3 decimal point as parameter. That is fine. In another, I think in fifth chapter you used 4 decimal points. It's okay, but you can still restrict to 3 decimal
Three
points
decimal
so that
points. Okay.
it will be uniform for all the things. Okay.
Okay. So okay,
So
sir.
that is one important point. You should keep it in.
Sure,
So
sir. Yes, sir.
otherwise, it is fine for me. Okay. So the requirements of that is Madras University for thesis submission. If everything is satisfied, then there is no issue with it. Hmm?
Yes.
Okay, and you try to complete the other paper so that, because see, when after defending your viva, then you will forget about the paper.
Okay.
Yes. Yeah, that is
Okay.
important. Yeah, you have to
So
concentrate
it
more.
is because we have done. I have still my from my thesis at least two papers I would have written, which is left out. So it is for you, because
Okay, sir.
fortunately I got a job, no issue. Okay, so you have to have the maximum paper possible. Hmm?
Sure, sir. Okay,
Okay,
sir. Sure,
okay,
sir.
yeah.
Okay, Cindy, your comment.
Kamalakannan, just
Sir,
to ask you whether you are aware of the structural parameters. What do you mean by 6 sets SIC?
6H.
Ah,
Okay, sir. 6 is the number of bilayers, H is the hexagonal. Of course, silicon carbide having the different polytypes. So it is starting from cubic to hexagonal. Rhomo quadrat is also it's available. So around 250 types is there, more than that. So that's from here you can see 6H means 6 layers will be there. A, B, C, and again A, like this. We can see, sir. A, B, C, A, B, C, D, like that.
ABC, ACB.
ACB, ABC, ACB, and again it forms like ABC, ACB, ABC, ACB, like that. Structure is going on like that. So because of that variation of the growth parameters, different particular things, it's growing like this. So usually it gives the hexagonal structure. So of course, even though these hexagonal structures is having the cubic structures also, it's around hexagonal is 30% only. The remaining is cubic. We can see the hexagonality is 37%. The remaining 67% is cubic for this system. 6H material.
then, why you have not used XRD? XRD, I didn't see any XRD patterns.
Yes, sir. XRD, we done the XRDs also. We have the results, but it's single crystal. We got only pick single pick. Of course, if we want to determine that the percent sample, what's this, the purity or otherwise like that.
Because when Dr. Viswanathan defended a thesis, I could see some
Okay.
stacking faults. Stacking
Yes.
faults when you implant with ions, right?
Yes, sir. Yes, sir.
And they analyzed that also. So you didn't do that kind of studies here?
No, sir. Our aim is so for the Positron analysis and Raman, we have to stick with that particular one. So so that I didn't do that.
Concentrated on the defect studies. Yeah. So
Yes, sir. Okay, sure, sir.
and that could have added to your work.
Okay, sir. But we have the XRD result for the pristine and implanted samples because it's already amorphized. So that if we got the XRD, we will get the amorphous peak only. So after annealing 1000 degrees Celsius, of course, we have to take the XRD. So we are believing that, of course, the peaks will regain it because in Raman we got the very good peaks after annealing. So of course, in XRD is also give the same things. We are believing that. So the variation of the peaks and suppression of the intensity by using that one, we can correlate the results and the defects, nature of the defects like that. We can correlate it.
And what is the focus of your study, Ma? Because it is with some aim on application you would have done this, yeah?
Yes, sir.
So can you correlate with some applications?
Yes, sir. Of course. Mostly this silicon carbide, so usually for the high power and high temperature and extreme hardness we can apply it. Sir,
Listen this question. He is asking, what is the focus, objective of this work? Don't start your basics. Just give the answer.
Yes, sir. Of course. So our objective is to understand the disorder and the crystalline natures and what is the path is chosen after the implantation and annealing, how we can recover the defects and activation of the defects, and to find the type of the defects and the position of the defects, like in the depth wise things. So that's our aim. And defect dynamics, of course, defect dynamics simply.
Kamalakannan, your objective was to fabricate a diode, PIN diode or PN diode.
Yes, sir.
By implanting the ions of either P-type ion or N-type ion with the oxide layer. That's the objective. During the kind of implantation, what kind of modification happened to your system, how you are going to modify the system to make it a perfectly implanted either a P-type material or a N-type material or a insulate. That's the idea behind it.
Yes.
So you used a tool, either a Raman or Classical or something else, to identify how this kind of defect has originated and how we are getting cured. To be frank with you, you cannot be 100% sure that you have cured that entire damage in it. No. You have done only to certain level of temperature annealing, right? So beyond that, you have to do some more temperature annealing. You have to make the system perfectly as a 100% P-type or 100% N-type with the activation of dopants. Because activation of dopants is yet to be clarified from your work. We're
Yes.
not done any work on that.
Yes.
You implanted, that's all. But we cannot say that there is activated of a P-type or activated N-type. There is no indication from any of your results, right? You have done the intermediate studies of the type of defect which is caused. So
Yes.
you have to target on that, right? That's what he
Okay.
is asking. Regulation is asking.
Okay.
So you have to be very clear on what is people are asking and you have to give proper answer for that.
Okay.
So that is missing in your summary. Actually, summary you should focus on this kind of thing. Starting from objective and conclude that. Okay. See,
Sure.
any more questions from your side, Siri?
Your voice is not clear. I could not hear you properly. But what I would like to suggest is you be clear on your aim and summary
Yes,
and
yes,
conclusion.
it's correct.
Yeah, fine,
It's
fine.
correct. Okay, so I strongly agree with Mr. Rajaraman Venkatesh comments. Actually, Dr. Rajaraman has clearly told about some of the small mistakes he has done it. For example, in fact, I noted on the coexistence of broadening and Raman spectroscopy. In addition to that, you said slicing with the
Yes, sir.
our homemade slicing.
Low speed base
It
mode.
it is not slicing, it is called dicing. Actual technology name is called dicing.
Dicing. Okay.
Yes.
Okay.
People will never use slicing for any semiconductors. People always use a name called dicing, D-I-C-I-N-G.
Okay.
Okay, correct yourself. And like Rajaraman pointed out, you used name same system, which I can take as a 15 implanted system or 16 implanted system or anything. Among the 6 samples, no, I can. So you have to very explicitly say whether it's a 15 implanted system or 16 implanted system. Okay. When you present certain things, you have to be very clear on the type of the conventions you used, right? And of course, you have done the maximum work and you have done some very good presentation and results also, which is fulfilling for the submission of about journal 3 papers and conference also 2 papers. Have you completed your other things like any examination? No, you have not done any examination because you are a free scholar, correct?
Sir, of course, so I completed the MPhil programs so that we are exempted. We
You
got
are
exempted
exempted.
from that.
Okay, you are exempted. So we are not conducting exams for your quality.
Yes, sir. Yes, sir. But we done the training programs which is conducted by IUSC. 2 training programs based on ion implantation accelerators.
Yeah, that can be taken. That's all about because assets is not mandatory for your work. So this is your presentation, but your thesis should have something different, right?
Yes, sir.
So when you present certain things, you have to be very clear on the objective has to be carried over through your presentation. So people should have the understanding why this kind of things are happening, why is checking this kind of the defects with respect to the surface or up to certain nanometer. Beyond that, what is happening? All those things you have to tell very clearly. Even you are writing the thesis as well as in the presentation. Also. Some places there are a lot of things are missing. Okay. And your summary in future work, you have to be very clear. Like Venkatesh pointed out, your objective should be completed. Whether you have done something, if not, you have to tell what is in the future. So what is a small area which is as blocks that should be come as a future work, right?
Sure, sir.
All of this cannot be completely covered. That's my observation. That's good. Anything else, Rajaraman? Any comments on that? Any other comments?
No, I think it's you people have to ensure that everything is in order. And
yes. Yeah. Once you start writing the thesis, we can go through it.
Okay. And Kamalakannan, you have to ask whatever you need. So whether it is positron setup or accelerator, the schematics, everything will be there. People just have to give. Yeah, all are collaborator. No, you can ask Sundaravil, I want this. You will give it. Okay.
Okay, sure,
So
sir.
similarly, you can ask Ranjit or Abhaya and
Okay,
get
sure,
it. Or you can tell me what you want from positron or Raman. So we give whatever required schematic, photograph, or extra clarification. Everything you should take.
sure,
Okay.
sir. Okay,
Unless
sir.
you ask, we will not know because we are not going to spoon feed you. This has to be done.
No,
Sure.
that is important. Due to collaborative work, you have used the facility at IGCAR. Yeah,
Yeah.
so it is better to use those pictures.
Sure, sir. Okay, sir.
As he rightly pointed out, not from the internet. Seriously.
Okay, sir. Sure, sir. Okay, sir.
So we will prepare that mails and we will send for sign. I think you have to submit within 3 months. Kamalakannan, your thesis should be
Yes,
ready.
sir. Okay.
Okay.
Yes, sir.
That's right. I think there's no other questions. I think we'll conclude. Thanks, Dr. Rajaraman, for having spent time to evaluate his presentation and give some valid comments for his thesis writing, and validation also for this comment on some more, particularly XRD, why you have not done that. You have to substantiate properly. You have not substantiated the results properly. Maybe you can give a clarification. Okay, thank you all. Thank you for participating in this meeting.
Thank you.
Thank you.
Shivaji, this pre-synopsis, it's not a public one because normally for HPNI we conduct as a public.
We don't conduct public in our university. This will be a small within the DC members. Only the Viva is a public.
Okay.
That, nothing is public.
Fine. Okay.
We do it as a doctoral committee meeting. We do this as a doctoral committee meeting. Final synopsis doctoral committee meeting.
Yeah, for approving his thesis submission. For synopsis submission.
So Viva OC will be public.
Okay, fine. Thank you.
Thank you.
So nice to meet you all. All the best, Kamalakannan. Sorry.
Thank you, sir. Thank you. Thank you. Thank you. All the best, Kamalakannan.
Thank you, sir. Thank you so much.